Hi there. Good evening to everyone. First and foremost, thank you very much for attending this introduction to multi-skill SIP webinar. My name is Anas. I am from Cybernet Systems Malaysia Syndrome Hub. So as you all know, today's webinar is going to be about the introduction to multi-skill SIP for material design analysis. If you have any question at any point of this webinar, feel free to drop them on the chat box and I will try and answer all of them at the end of this session. So the agenda for today is first, I'm going to start with the introduction to Cybernet systems and followed by a little bit of introduction to ANSYS. And then we go to the introduction to multi-scale SIM. I'm going to tell you a little bit about the background and the motivation behind the software and also the function of the multi-scale SIM. And then I'm going to explain a little bit about multi-scale SIM by showing a case study. And of course, finally, I'm going to show a bit of a demonstration choosing the multi-scale SIM. And then we wrap this up with a Q&A session. First, let's start with a little introduction to Cybernet systems. Established in 1985, Cybernet System has been providing CAE solutions and also IT solutions in product sales, contract analysis, consulting software development for over 30 years now. We have developed a partnership with more than 20 companies, mainly in the United States, including ANSYS, Synopsys, and Symantec. Our head office is in Tokyo. The sales subsidiaries of Cybernet consist of Cybernet China, Cybernet Taiwan, Cyfam, which is based in Korea, and of course, Cybernet Systems Malaysia. Here, as you can see, Cybernet System has been working with numbers of group companies around the world for both sales and also development. So a little introduction about Cybernet Systems Malaysia. Cybernet Systems Malaysia is in KL Eco City Bangsa and has been around for more than a year now. Cybernet Systems Malaysia was established in November 2018 as the fourth subsidiary in Asia. Our business here mainly revolves around CAE solutions, IoT and big data solutions, and also professional services. Our partners up until this point in time include ANSYS, Synopsys, and many others. As you all know, Cybernet Systems provides all sorts of solutions. Now, those solutions include CAE solutions, visualization solutions, big data solutions, IoT, digital twin and AI service, IT solution, and finally, an engineering services. So a little bit introduction of ANSYS. Founded by John Swanson in 1970, now ANSYS Incorporation is a global public company based in Canonsburg, Pennsylvania. It develops and markets multi-physics engineering simulation for product design, testing, and operation. As you can see here on this slide, those multi-physics include almost every conceivable physics analysis you can think of, ranging from a simple structural analysis all the way to a system simulation. Now, for 50 years, ANSYS has been a class-leading multi-physics simulation software provider. Due to that very fact, ANSYS now has been used worldwide with over 45,000 global customers. ANSYS is also used in a wide range of industries, including automotive industries, electric and electronics, aerospace, and many more. As I said before, ANSYS provides multi-physics simulation for every type of needs. Those simulations include mechanical solution, thermal fluid solutions, electronic solution, design solutions, which is mainly for designers, and some additional options which include a parallel computing module, material data selection, analysis tools, and so on. So now we get into the multi-scale SIM. Now, what is the multi-scale SIM exactly? Now, the reason why I explained about ANSYS in the previous slide is because Multiscale is an add-in tool for ANSYS Workbench environment. Developed by Cybernet System Japan, Multiscale SIM can perform a numerical material test on composites to evaluate macroscopic anisotropic material constant without having to carry out an actual physical material testing. The way multiscale SIM perform this numerical test is by using the homogenization analysis for the multiscale modeling. Now, in essence, the principle behind this multiscale SIM is based on a method of multiple scale used to derive average equation of a much larger scale from consideration of the small scale. Now, before we go deeper into the multiscale SIM and its features, let's learn the motivation and background of this software first. First of all, what is composite? So basically, a composite is made by physically combining two or more material or components to produce a combination or blend of structural properties which is not present in any individual components. They can, for example, provide a greater strength and rigidity than is found in any of the separate components while being as light as possible. As you can see from the slideshow here are several examples of composites. For example, fiber reinforced plastic is a composite material made of polymer matrix reinforced with fibers. The fibers are usually glass, carbon, or aramid, and the polymer is usually an epoxy, vinyl ester, or polyester thermosetting plastic. And also PF resins are still in use. Now, FRPs are commonly used in aerospace, automotive, marine, and construction industries. On the other hand, porous materials such as a faux, lattice, and even perforated metal here can somewhat be categorized as composite material as well. The consecutive presence and absence of a material make it function like it's composed by two different materials and behave anisotropically or orthotopically. So a survey conducted by NAFAM's Composite Working Group showed that many AVA analysts often struggle the most when it comes to find a proper materials data for composite materials. Now, this matter is truly understandable as composite material comprised of two or more materials, and the configuration of those materials may vary depending on the purpose. To find the material properties exactly like the users want can be challenging. Therefore, this is one of the motivation behind the multiscale SIM software, as I will explain later on. Multiscale can perform a numerical material test and accurately predict the material properties for almost any kind of composite. So what are you seeing here on the slideshow right now is basically a representation of several difficulties when it comes to modeling composite material in material design. It is basically divided into three. First, defining material properties of the composite, and then there's a difficulty in the finite element modeling of the composite and also the post-processing. Unlike isotropic materials where the material properties are the same in every direction, anisotropic materials have a different material property depending on the direction of the material. And therefore, when it comes to model the material itself, it is difficult to know exactly what is the material properties in any given direction without experiments. Like I mentioned before, the material properties are also depending on the composition of the composites. Say, for example, the percentage of the fiber relative to the filament in any given volume. Material composition plays a big part in structural behavior of the composite materials. Therefore, it is important to accurately model the material. Now, when it comes to finite element modeling, analysts usually stumble upon several difficulties. For example, a full structure of composite usually comprises of super thin layer of material or a very small hole relative to the whole model. Now, the scale of the microstructure to the whole model is huge, causing the problem when it comes to meshing process of the model. Plus, because of the composite material possesses anisotropic material properties, fiber direction or distribution need to be taken into consideration as well, as it plays a large role on how the composite structure will behave under certain loading or boundary conditions. And then, of course, when it comes to evaluate the result during post-processing, problems such as finding a failure model to base on for any particular composite material can be a problem as well. Again, it is because composite material behave quite differently from a typical material, isotropic material. For example, predicting a fracture origin, such as a fiber breakage or delamination of a composite. Now, accurate prediction of structural characteristic is a challenging problem in FEA due to its orthotropic structural behavior. Therefore, multiscale SIM is aiming to tackle this type of difficulties. Now, especially when it comes to model the material properties of the composites. So here we have a printed circuit board or PCB. So PCB is one of those products that mainly constructed or made mostly out of composite materials. To accurately evaluate, for example, the thermal or structural performances of the PCB, close enough material properties defined in FA is not good enough. Therefore, having a tool to evaluate the composite material properties for each of the components of the PCB will significantly help in evaluating the performance of the PCB, subsequently improving the products. Here, for example, as you can see, the base material for the PCB is made of FR4 epoxy laminate and also a prepreg. As we all know, the most accurate way to evaluate material property is by doing material testing in experiment. The problem is a certain material test can be time consuming. For example, a grit test, like you can see on the screen right now, can take months and even years to extract any useful data and information. One can also easily find themselves caught up in an expensive material testing bill. A single material test for one specimen can easily cost more than $100. Plus, the effort to make a material specimen can eat up quite a lot of resources as well, especially when you compare with what can be achieved with virtual material tests. So now let's dive into the features available in Multiscale SIM. Now, what kind of function does it have to help in material design? Like I mentioned earlier, Multiscale SIM can evaluate material property of composite material. It can be achieved by having the function of model creation, virtual material test, and also curve fitting. Now, model creation allows the users to freely model the microstructure of the composite. The users can either model the microstructure themselves, or the users can simply use the Multiscale SIM template available inside ANSYS Design Modeler and ANSYS SpaceClear. Now, this template contains 17 different configurations of microstructure to choose from, including, for example, unidirectional fiber, crossweave, particle dispersion, and even honeycomb. The users can freely modify the dimension of the microstructure as well. So now we have the main features of Multiscale SIM. The virtual material test, also known as homogenization analysis. This is how the users can evaluate the material properties of the composite materials. It is done by performing a homogenization analysis on the microstructure that the users use, that the users just define during model creation process. Multiscale SIM allow the users to be flexible when setting up the boundary condition as well. Now, after the virtual material test was done, a report for material response will automatically generated for the convenience of the users. Now, the main advantage of Multiscale SIM is that it can include the nonlinearity of the model in the analysis. And then finally, we have the curve fitting function, which allow the users to use any type of material model for their composite materials. The curve fitting analysis is performed in order to evaluate the material constant for any material constitutive law. Like I mentioned previously, the main function of multiscale SIM is the homogenization analysis. Now, what you can see here on the screen is a schematic diagram to explain the procedure to evaluate a material constant using multiscale SIM. So you can get a microscopic anisotropic material constant as the result of this analysis without doing a real material testing, like I mentioned before. The blue-colored box here are the input needed from the users, while the red-colored boxes here are the output, so to speak. So in the first step, the users must first create an FE model or define the geometry parameter for the microstructure of the composite based on observation results. Like I mentioned before, multiscale SIM provide many templates to create a microstructure, which is embedded in ANSYS Design Modeler and also ANSYS Space Claim. Now on the right side of the screen there, as you can see, is the microstructure templates integrated inside ANSYS Design Modeler. You can also see the detailed view under here, of which the users can specify the dimensions and the compositions of the microstructure. Another input from the users is the definition of the material properties for each part or components of the microstructure. The users have to specify the material used for each component of the composites. For example, for fiber reinforced plastic, the users might first define a material property of epoxy resins, and then another material, which is the glass fiber. Now, after the users have done with DFE modeling and also material properties definition for each part, the users can now perform the numerical material testing for the microstructure model. For example, if you want to know the anisotropic elastic constants, Multiscale SIM will perform the test for 6 deformation modes, which are uniaxial test and also pure shearing test. On the slideshow here is the example of the results of the uniaxial test and also the pure shear stress. As a result, the users can evaluate macroscopic material response as stress strain curve, which is then used to evaluate the equivalent material properties via the function that I mentioned before, which is the curve fitting function. Now, the curve fitting analysis is performed in order to evaluate the material constants for any material constitutive law. All of these procedure setting can be performed in ANSYS mechanical GUI. So therefore, the users are not required to learn any new operational procedures if they're already an ANSYS user. But if the users are new to ANSYS, the learning curve for ANSYS is not really that steep in my opinion. So the new users can understand how it works quite easily, especially with ANSYS Workbench. That is actually one of the major advantages of ANSYS. So here we have another feature of multiscale SIM called localization analysis. Here the users can observe the distribution of any results item in microstructure level at any point of macroscale model. For example, here, as you can see, we have a macroscale model undergo a 3-point bending test. The material is a unidirectional reinforced plastic, and the fiber orientation is parallel to the longitudinal direction. The microstructure is homogenized by using the homogenization analysis, as I mentioned in the previous slide. Now, the microscopic failure threshold is also prepared by the same technique. The picture on the far left-hand side here shows the distribution as the result of microscale model. In this case, the user is interested to know the failure origin on the microscopic level. So there's a point 1 and point 2 were selected for the localization analysis. Another two pictures here are showing the failure progress in microstructure at those 2 points. Point 1 means the bottom layer, and point 2 means the neutral plane region of the macroscopic bending specimen. So you can confirm that the bottom layer is failed by fiber breaking. On the other hand, the neutral plane region is failed by transverse clad, which is cause of debonding at the interface of fiber and also resin. Now, this analysis technique is similar to submodeling technique, which is an original function in ANSYS. Submodeling technique, a real analysis object are divided to model and submodel. So as an important point, these two models have the same size scale. On the other hand, localization analysis divides the object to macro and micro model. So the scale of two models is completely different. The macro model has the order of, say, centimeter or meter, whereas the micro scale model has the information in the range of micrometers. So submodeling technique cannot be applied to this problem. So this is basically just the summary of the typical workflow of multiscale sim. So we start with our microstructure design, then followed by a material definition for each part of our composite. And then we perform the numerical material testing or homogenization analysis on the microstructure to evaluate the material properties of the composite material. Now, from here, we can either finalize our analysis with a macroscale analysis and final design, or we can continue with the localization analysis. Say, for example, if the user's interested to study the microstructure behavior from our macroscale model. Now, this final part is really up to the users, basically. And then here are some of the microstructure models which can be created using modeling template of Multiscale sim. As you can see, Multiscale sim support many types of composite microstructure. Now, not only fiber reinforced composite, but also other composites such as filler dispersed or even polycrystalline. Now, almost all microstructure are supported by Multiscale sim extension for design modeler, as I will show you later on in the demonstration. So here on the slide right now are the supported material models in Multiscale. There are two types of license in Multiscale. The first one is a linear license and the other one is a non-linear license. Now, linear license allows the user to access to only the linear analysis. Now, while the non-linear license gives access to every features of the Multiscale sim. Now, with structural analysis, users can have access for many different material models, as you can see right here on the screen. Now, that model, the models such as elastoplastic and also creep also can be done with Multiscale sim. So if you look at the table right now, almost all material models support orthotropic material property. So here is actually the case study that actually apply the usage of Multiscale sim on the analysis. Here, as you can see, is a case study for a perforated metal. Like I mentioned before, perforated metal consists of a very small hole which is perforated through the metal. Now, the users are interested in reducing the analysis cost and also analysis time from the analysis. Now here we have the homogenization on this area right here. Now, because of the homogenization analysis that have been done on the perforated metal, the users can actually know the material properties of this region right here. And then from the gain of the material properties, it used to make this metal right here, and then just simply use the material properties that has just been generated. Doing so will reduce the amount of meshing. As you can see, the difference between elements and node of these two models, it is significantly lower compared to the full model, which include the perforated region of the metal. And then subsequently, you can see that the analysis cost was reduced significantly. The reduction can be seen at, it's recorded at 96%. And then we continue comparing the error between the two models, the direct model and also the homogenized model. The error is actually below the 2% when comparing between those two models. Therefore, it is an acceptable amount of error considering how much analysis cost and analysis time that you can reduce by performing the homogenization analysis on the perforated metal. So finally, we are going into the demonstration of multiscale SIM. So as you can see right now on the screen, we have two types of analysis that I'm going to demonstrate. For the linear analysis, I'm going to include the homogenization analysis, and then followed by a macro model analysis, and then localization analysis. Then for the nonlinear analysis, I'm going to do an elastoplastic homogenization analysis. Now, for the homogenization analysis, the goal is to determine the homogenized material properties. And then from that material properties, we are going to use it to do our macro model analysis right here. And then finally, we are going to do a localization analysis using the macro model that we've just analyzed before, and then to evaluate the microstructure of the full macro model analysis that we've done before. And then finally, we are going to learn a little bit about one of the examples of the nonlinear analysis that you can do inside multiscale SIM. For elastoplastic homogenization analysis, we are going to evaluate the stress strain characteristic of the material. And also we want to identify the material constant by performing the curve fitting. So first, I'm going to show you how to launch the multiscale SIM. So to launch the multiscale SIM, you go to your start, and then you can see here you have the multiscale SIM launcher. And now you can select which version of the multiscale SIM you want to use. Now currently the latest one, multiscale launcher version 2.1 is available with ANSYS 2020 R1. Therefore, that is the one I'm going to pick. And then for the license, I'm going with the non-linear license. And then for the environment, I'm just going to focus on the workbench for today. And then I just simply click run. And then it will launch the ANSYS, the version that you've just chose. So after launching the multiscale, we are actually presented with what we call the ANSYS workbench. So on ANSYS workbench, we have this white region right here, which is called project schematic. And then on the left-hand side right here is the analysis system, of which you can choose whatever type of analysis that you want to do. So for this example, I'm going to use a static structural analysis throughout the demonstration. So to use or to launch the multiscale sim, first we have to go to the extension, and then you go to the manage extension here. You need to activate the multiscale sim here on the extension manager. As you can see, I've already done it before. After you check these two box right here, you can simply close it, and then the multiscale is ready to use in your ANSYS environment. And now for the first demonstration is the linear analysis, or the homogenization analysis of our microstructure. So I have actually done the example beforehand, because the calculation time can take quite some time to finish, and therefore I've done it in advance. But I'm going to walk you through the step-by-step procedure on how you want to do the homogenization analysis and other type of analysis with multiscale sim. So the first one is the homogenization analysis. We are first going to drag this static structural analysis in the white region project schematic. And then next step, like I mentioned before, the first step is to define the material for each of our components of our composites. So to do so, we go to the engineering data right here. Then we go to the engineering data sources. And then we want to scroll down until we find the multiscale folder here. We click it. Then we have different type of material that we can choose from. Now for this particular example, a linear analysis, the homogenization analysis of a linear material, I'm just going to select the epoxy resin elastic, and then also the glass fiber as well. So our composite will be comprised with these two materials right here. Then I simply click close. And then next, what I'm going to do is actually model the microstructure. So how am I going to do that? I'm going to right click here on the geometry, and then go to the design modeler. Right now, launching the design modeler. This is where you actually create the microstructure that you want to analyze. Now, like I mentioned before, you can either make it yourself, or say, for example, you already have a CAD data for a microstructure that you want to analyze. You can simply import it into the ANSYS environment. So right now, I'm just going to create a simple microstructure. First, I'm going to change the units into millimeter. And then for this particular example, I'm going to use the unidirect material microstructure. So after I click this, then you see here already included in our tree. Now under the details view on the definition, I can change the volume fraction of my fiber compared to the whole total volume of the microstructure. In this case, I'm just going to maybe use 40% volume fraction of the fiber, respective to the 100% volume fraction of the filament. Now you can either define or not the fiber diameter. In this case, I'm not going to define, because it is okay as long as you define this part of our model right here. Then I simply right click on the unidirect and then click generate. Now as you can see, our microstructure has already been generated. We have the filament volume fraction here. Then on the inside, we have our fiber, which is 40% compared to the whole microstructure. After I've done define my microstructure, I'm just simply going to close the design modeler and then go into the modeling or pre-processing of ANSYS. Right now we are starting the mechanical, ANSYS mechanical, as you can see on the bottom left hand side right here. So now our microstructure has successfully been imported into the ANSYS mechanical environment. First, what I'm going to do is go to the geometry and then expand this unidirect object and then define the material that I want to use. For example, the outside here is the filament, which is I am going to use the resin. And then for the fiber, I'm going to use the material glass fiber as the material. And then next, I'm just simply going to mesh my microstructure. So here we have a fairly fine mesh for our microstructure. And then for the next part, how am I going to start with the homogenization analysis is by clicking on the static structural right here. And then I click on the Multiscale Sim tab on top. And here, as you can see, is basically the option of multiscale function inside ANSYS Mechanical. These three here is for linear analysis. And then these two here is basically for the nonlinear analysis. Now, because of this is homogenization analysis for the linear material, I'm going to click on linear and then click on homogenization setting. What it does is basically give us the option to select the homogenization type that we want to use. Now, the user can either select or use this one, the elasticity density thermal expansion, which means if you select this, the output, you can have the output as the elasticity, density, and thermal expansion as the material properties. Or you can also select this one, the integrated cross-section stiffness as the output. Or you can also select seepage flow coefficient as the output. So in this case, I'm going to select the first option. And then on this here, on this region, on this place right here under the definition, this is where we name our material that we've just made. For example, this is where we export it into a file which we can use later on to model our macro model. So for example, for this material, I'm just going to name it material test 1. And then also you can include the material description for the material that you want to make. And then on the .NET file here, I'm just going to click yes. This is basically we tell the system to export the material data. And then you just right click here on the static structural, and then you just click solve to initiate the homogenization analysis. Now, because I've done this before, I'm just going to show the results straight away. Okay, so this is basically the same example that has already been calculated. So we've done with the homogenization analysis. Here I name the material as mat test 1. And then I put a material description of 50% fiber, because this case I'm using a 50% volume fraction for the fiber. And then what I'm going to do next is click here on the CMAS homogenization. When you do that, here as you can see, our material properties has been generated for this particular microstructure. Here we have the Young's modulus for each direction. Because this is a composite, it is an anisotropic material, and therefore you have a different type or different value of material properties depending on the direction. Now in this case, you can see the x direction having the value of 3.8 times 10 times 10 to the power of 10. Comparing to the y and z direction, which is only just 1.13 times 10 to the power of 10. So this is basically an orthotropic material, because two directions having the same value, while only one direction having a different value. So here, as you can see under the material properties, we have the Young's modulus, shear modulus, and also the Poisson ratio. And then also we also have the elastic matrix of our material that has been generated as well. Then we are going to visualize each of the material testing that this microstructure has been gone through. So how I'm going to do next, I'm going to the multiscale.sim tab again. And then on the elemental result, I'm going to select stress. Here, as you can see, it will display a stress, which is stress from the test of the uniaxial tension in x direction. And then what I'm going to do is I'm going to input another 5 of those results. Then I'm going to change each of this one into a different direction. This one I'm going to change into Z direction. Then for the next 3, I'm going to change it into a pure shear test for each of the plane. Then I'm just going to simply right click here and click on evaluate the results. Because this is a post-processing and therefore it will not take too much time. Now we can view each of the stress tests that has been going on our microstructure right here. Now you can even animate the deformation or stress of our microstructure, because this is one of the features of ANSYS. It can animate whatever happened on your model and therefore help the users to understand the model or understand the result even more. So there is another advantage of using ANSYS. Then of course we have in the y direction, in the x, in the z direction as well, and of course the shear test. Now from this test is where these material properties is extracted, information is extracted from, and therefore this is how it gets this material property. So this is basically what it means by homogenization analysis. From a microstructure, you run a several tests on it, and then it gives out an output of material properties for the particular microstructure. And then the material properties can be used for a much larger scale model or a macro model. So next we go to the macro analysis. Now as you can see right here, we've already done the homogenization analysis. And then if you see here on the engineering data, I've already included the material test, the mat test 1, which is the name of the material that we've just made and what we just get from the homogenization analysis just now. Now, using that material test data, we are going to apply it to our geometry. Now, this macro model geometry has already been done in advance. So here is our model. As you can see, we have a sandwich composite, or so to speak. We have this top and bottom side of our model, and then the middle side, we call it core. Now, if you can see right here, the way I want to model it is for the fiber to run in the longitudinal direction for the skin, top and bottom. And then for the core, I want the fiber to run on the width direction of the model. So how am I going to do that inside our macro model? Because here, as you can see, there's no physical or actual fiber that's been included in our model, because already been homogenized, and therefore we are just going to use the material properties. Now, to do so, I'm just going to change the coordinate for the core right here for the x direction to be facing, or facing y direction of the global coordinates. And therefore, because this is the principal axis for the fiber, and therefore it will run according to the direction of x axis. By doing so, we'll make the fiber to run on the width length of our whole microstructure, our whole model. Then again, I'm defining this material using, I'm defining these parts using the material model that I've just made, which is the mat test one. As you can see right here on the core as well, and from the top side as well. Next, I'm just going to simply mesh our model. For this, I'm actually trying to simulate a bending test for this particular model. This is basically actually a half model, which is symmetry on this plane. So you can imagine there's another similar block on this side right here. By doing this, it can basically cut the simulation cost into half. And I also put a displacement in the middle to simulate a bending test. And then we have this as a result. So this result is basically came from the material that we've just made from the homogenization analysis. So next, what I'm going to do is walk you through the localization analysis. So basically, how to do a localization analysis is you go to this Multiscale tab. Right here, we have the localization tab. Then click on it, and then we simply click on extraction. So, for example, I want to study this microstructure on this region right here. I'm just simply going to select this, then click apply. And then I'm just going to right click and then click on evaluate all the results. And as you can see, I've already extracted this particular region to do the localization analysis on. You see the strain has already been extracted. The strain value on that particular region has already been extracted. But what I'm going to do next is actually see the microstructure behavior of our model. So what I'm going to do, I'm going to drag static structural analysis and then drop it into the model cell on the A cell right here. Then simply double click on it. Okay, so as you can see right here, we already get our microstructure here. And then from this static structural analysis, what I'm going to do is go to the localization tab again, and then click on localization setting. Now here, as you can see, we already have the extracted element or extracted microstructure that we've done before. We already also have the strain value for that particular microstructure. And then on the solution, I'm just going to simply insert a equivalent stress as the result. Then I'm just going to simply right click, then solve this. It can take quite some time depending on how fast your computer is, for example. After we've done this calculation, it will show the equivalent stress on that particular microstructure from the one that we selected on the previous analysis from our macro model. Okay, so now the calculation we have done, we're going to view the equivalent stress that's been going on that particular region. So as you can see, it's actually undergo a sort of a tensile. It's put under tensile stress because it's placed right at the middle of which the bending is occurred, and it's actually at the tension region of the whole macro model, and therefore you see on the microstructure as well is currently having a tensile stress applied to it. So that's basically what is meant by localization analysis. From a macro model, you extract one microstructure to view what is going on the microscopic level. So finally, we are going to see take a quick look on the nonlinear analysis featuring multiscale sieve. Now, in this case, it is a elastoplastic homogenization analysis. Now, as you all may know, elastoplastic is one of the nonlinear material, and therefore we need a nonlinear analysis for this part. So how the basic procedure is almost the same as when you are doing the linear analysis, but the setup is a bit different. So I'm going to show you how to do it. Again, I'm going to drag a static structural analysis inside the cell. And then I'm just going to connect these two, basically using the same engineering data as I used before. Then I'm going to open the model as well. So again, our model has already successfully been imported into SYS Mechanical. Now let's see the material that we're using. So for this outside right here, instead of using nylon elastic, I'm going to use the nylon elastoplastic for this case. Then for the fiber, I'm just simply going to use the carbon fiber as the material. So this is basically a combination between a carbon fiber and also an elastoplastic material. Then again, just simply mesh our model right here. So here we have already mesh. And then here, instead of going to the linear homogenization analysis setting, we are going to this part right here, which is numerical material testing, which basically means a homogenization analysis for nonlinear material. Then I'm going to select this parameter identify set. It's basically to run a test according to material model to be homogenized. And then after you click that, you are presented with this setting window right here. Now here you can select either what kind of material that you are using. In this case, I'm using elastoplastic. Therefore, I'm going to select elastoplasticity for the model that I'm going to use. You can also select viscoelasticity, creep, and also hypoelasticity. Then I'm just simply going to click this create system. After you click that, as you can see, it automatically generates this 6 more analysis windows right here. This is because it is required to do a material testing, and therefore each of the tests does require each of its own analysis window. For the nominal strain value, I'm just simply going to input 0.1. The number of steps, just simply going to input 25. And I click OK. It will automatically set or pre-processing your model. So now as already been set, you just simply click here on the model and then you click solve to start the homogenization analysis for your nonlinear material. Now this one will take quite some time because it is a nonlinear analysis and therefore it takes a little bit more time. Now before you run the analysis, you need to quickly change on the analysis setting for each of the analysis. And then you see right here on the large deflection, we need to turn this on for each of the analysis, turn on, so on and so forth. And after you've done that, you simply click solve, and then it will find the homogenization. I will run the homogenization analysis as you wish. Now let's review what is the output from the homogenization analysis for the nonlinear material, which in this case is the elastoplastic material. So this is what I've done before. As you can see, all has been, the icon is a green check mark, which simply means that it's already been solved. Then here you can see a nonlinear homogenization analysis setting. So I'm just going to delete this first. Now after you've done that, you can see there's a macro response results. Now this is where the stress strain curve being generated or being extracted from each of the material testing, depending on what kind of test that is already done. For example, this macro response result, is the material testing for uniaxial tensile test on the x direction. Now in the x direction, the strand predominantly coming from the fiber, which is an elastic material. And therefore the stress strain curve right here, as you can see, is a linear curve. But when you take a look at the tension on the y direction, the graph here, the stress strain graph here is actually a curve, because on the y direction, the stress predominantly coming from the filament right here, which is our nonlinear material. Same goes with the z direction as well. And then next, after you get this kind of result, we are going to do a curve fitting using the curve fitting function inside the multiscale C. Now how we're going to do that, we go to the solution right here. And then we are simply going to right click, insert nonlinear homogenization setting. And then here is where you need to specify the plastic strain value at where you try to fit the heel stress. Now in this case, I'm just going to say, for example, 0.03. And then here in the engineering data section right here is where you want to export all of this data into a usable material data. Maybe the next time you want to use this, you can simply find it in the engineering data, like I mentioned before. So like before, you simply put a name, and then put some material description, and then export, you click apply. And then you simply right click here and then click generate. Now it's already done curve fitting. Now we want to view it by clicking on nonlinear and then select the curve fitting result. Now here, as you can see, you can ignore the tensile test on the x direction because it is actually a linear. And as you can see, this is basically what the graph looks like when you apply the curve fitting function. Now after you've done this, this is where the material properties is been extracted from. After you've done the curve fitting on the homogenization analysis results, we can get the material properties for our nonlinear material right here.